Well, hello there. This video is by Dr. Craig Hane here, and it is aimed at anyone interested in high school math education. And the topic I want to talk to you about is rigor versus intuition and heuristics, because I think this is a very important topic for math educators to be thinking about, because we have a real problem today with our standard math curriculum, and there's a lot of things that you need to understand about it. Well, first of all, when you say rigorous in mathematics, what that means is you're going to be proving a statement using a finite series of steps, logical, from already proven statements or from axioms, and that'll be called a proof. And modern theoretical mathematicians don't consider something to be true until it has been rigorously proven. Now, a proof might make it easier to understand a concept, or it might not make it easier. In fact, many proofs in mathematics are very hard to follow, and in fact they don't make the understanding of a concept any easier. I give an example of that in one of my other videos on Pythagorean triples. I show you a proof where I don't think it helps you understand it at all, then I show you how to approach it in a way that you do understand. Proofs very often don't do that, and if a proof doesn't do that, I don't think it's of any value in educating a high school student. Now, intuition in mathematics is where you understand a concept or a statement of math with some kind of reasoning or metaphors or experiments. And it's hard to define intuition, but it's when you just feel like, well, this must be true. Now, sometimes you're right and sometimes you're wrong. Sometimes the statement that you intuitively think is true turns out to be true, and sometimes it's provable, but sometimes it isn't true or provable. In fact, you can have true statements that aren't provable, but that doesn't happen very often. So you've got to be careful with intuition. It can lead you astray, but if you're dealing with something that's pretty well understood by mathematicians in general, your intuition is probably going to be very good for you. Now, heuristic means where you're thinking to understand a concept or a statement intuitively and do a series of intuitive steps to understand it. So intuition and heuristic thinking sort of go along together. Now, I'll tell you this, most mathematicians, I believe, it's been my experience talking to them, and what I've done myself, is discover and learn new math concepts, and that's two different things, but it's kind of the same thing. When you learn something new, you've discovered it, even though maybe other people knew it. But we do that intuitively. And then later, we try to prove it heuristically. In other words, we try to come through a logical argument we think is true. And then, once we've done that, if you're a theoretical mathematician, you can tackle it rigorously. And rigor, of course, is much harder to do. Rigorous mathematics is not easy at all. And by and large, only theoretical mathematicians really care that much about it. In fact, rigor really didn't get started until the 19th century. It was in the 1800s when it started. Mathematicians up until then pretty much did things intuitively and heuristically. Euclid's Elements was the first attempt at rigor, but modern mathematicians consider that it was pretty inadequate in many ways, but it really got it started. And if you study my video on what is math, it's axiomatic systems. You start with axioms and undefined terms, and then you rigorously prove statements. But first you have to discover what you think might be true intuitively and heuristically. Now, for example, our old ancient ancestors, thousands of years ago, probably discovered the Pythagorean theorem intuitively. How? Well, they probably just calculated the squares of the sides of a lot of right triangles. And they always found out that a squared plus b squared equals c squared, as close as they could calculate. And they did that probably with lots and lots of right triangles. Well, it must always be true. If you've tried something experimentally 100 different times and it always turned out the same way, then you know, well, that's probably always true. Now, that's a heuristic understanding, intuitive understanding. And I will tell you this right now. Many scientists and engineers, I don't want to say all, but I say most scientists and engineers really only understand concepts and mathematics intuitively. They leave the rigor to the mathematicians. When I taught at engineering school, I can tell you right now, the engineers didn't much care about the rigor. They just wanted to know intuitively and heuristically what was true so they could apply it to engineering. Now, the Pythagorean theorem is very easy to understand intuitively, and it's very easy to apply, and it's very valuable to science and engineers for those reasons. The first known rigor proof of it was back in Euclid's Elements, 2,500 years ago. It's Proposition 47 in Book 1. And that was the first rigorous proof that I know of for the Pythagorean theorem. And I will tell you, that proof in Euclid's Elements, you ought to look it up sometime. It's difficult to follow. It's based on what's called the windmill diagram. And I talk about that in some other videos on the Pythagorean theorem. Very few people can follow that. And worse than that, it doesn't really help you understand the Pythagorean theorem any better or how to apply it. It's a proof, but it doesn't really add much to you to understand it. At least it didn't to mine. Now later on, mathematicians started using other tools like algebra, and they came up with much simpler proofs, and that was really great. As a matter of fact, I came up with the simplest proof I've ever seen using similar triangles. 3-line proof. Great. But of course I had to know something about similar triangles. Now many mathematicians over the centuries thought that if you just took the axioms of Euclidean geometry and didn't include the parallel postulate, that you could still prove the Pythagorean theorem. It would always be true. Well, guess what? And that went on for centuries. They were wrong. In fact, we learned that in the 18th century, and I have a whole video on the Pythagorean theorem. Is it always true? And the answer is, it's not always true. As a matter of fact, it's usually not true in most geometries. It's only in a very special geometry, Euclidean geometry, where it is true. And I have a whole video on that you might want to watch. Now, most math discoveries, I believe, were made via intuition and experimentation. You experiment, like I just mentioned with Pythagorean theorem. I'll give you another example of that. Back in the early 1600s, a famous mathematician by the name of Fermat, F-E-R-M-A-T, he proved a bunch of theorems, and he notated them in his book that he had, and he didn't really give the proofs, but he would say, I proved this theorem, and later mathematicians would come along and prove them. Well, the last one in his book that he claimed he proved was, we now call it Fermat's last theorem. And we don't know how he came to believe it. Maybe he did some experimentation, maybe it was intuition. He never supplied proofs of his theorem, he just said he had them. And it seemed like a reasonable thing, and most of his other statements he said he proved were true. They could prove them. So we'll be able to prove that. And they tried, and they tried, and they tried for almost 4 centuries. Unbelievable. And it was hard to prove. They couldn't prove it. Now, it's something that seems, well, it could be true, and it's the kind of theorem that you really don't know. I mean, it could be true. Well, it turns out that right near the end of the 20th century, in the 1990s, I believe it was, finally, a brilliant mathematician, Andrew Wiles, used some very, very sophisticated and complex mathematics, way beyond anything in Fermat's era, to prove it. And Fermat's last theorem was finally proven. And I have a whole video on that will talk about that, and you can watch that. It's an unbelievable thing. Now, there's a great book on this called Vermonts Enigma by Simon Singh, and I highly recommend you read it if you're interested in theoretical mathematics. If you're thinking of maybe becoming a theoretical mathematician, I recommend you read this book, because you really need to get an idea of what it's all about for mathematics. Mathematicians spend lots and lots of time intuitively and heuristically analyzing things, and then they try to prove them rigorously. And it is much easier to figure something out intuitively and heuristically than it is to do it rigorously. Mathematicians didn't start doing rigor, like I said, until the 1800s. Now, here's my belief. I'm a high school math teacher. I believe at the high school level, when you're just beginning to learn math, you should strictly use heuristics and your intuition. Develop your intuition, learn how to use heuristic arguments. Now, a heuristic argument can be very logical, and it needs to be. But along the way, you got to make a few assumptions that are reasonable, but they would be difficult to prove rigorously. And I do that throughout the treatment of all sorts of subjects then as we go through it. And I'll talk a little more about that in a minute when we get to calculus. But I'll give you an example. In Tier 2, which was our very first time we're teaching students anything about geometry, it's our very first approach to geometry. We're just teaching them the practical things. We really prove several theorems heuristically. For example, really early on, I prove heuristically that the sum of the angles of a triangle is 180 degrees. That's extremely important. That's one of the most basic things you learn in geometry, and you use it all the time, over and over and over. And it's very, very easy to prove heuristically. In fact, it's not too far from a rigorous proof, to be honest about it, but some rigorous proofs are easy, and that's great. Now, I mentioned earlier the Pythagorean theorem. It turns out it's easy to prove using similar triangles, like a three-step proof. I discovered it myself. I'd never seen it anywhere, and I thought, wow, that's great. The best proof I've ever seen, and I was really kind of proud of myself for doing it. And of course, somebody surely has done it. Well, then later I was reading, and guess what? Einstein. That was the proof that I either discovered or found, and it's what he found it was the best way to understand the Pythagorean theorem, and I think it is. Furthermore, it was that proof using similar triangles that let me fully realize that the Pythagorean theorem is not true in a non-Euclidean geometry. And I have a whole video on that, and so you can watch that. That's very, very easy to see. Now, I mentioned earlier that similar triangles is what I use in my great proof, but a rigorous proof of the equality of the corresponding ratios of two similar triangles is actually quite difficult. It's easy to understand intuitively and to believe it, and it is true. It has been proven rigorously, but it's not easy to prove rigorously. At least I've not seen an easy, rigorous proof of it. I don't think Euclid did it rigorously as it could. Now, when we get to calculus, which is extremely important if you're interested in going beyond basic math, if you're going into STEM, calculus, of course, is the key tool used to analyze functions, and functions are the model for STEM. I talk a lot about that in other videos. Well, our ancestors used something they call infinitesimals, infinitesimal number. An infinitesimal number is a number that's smaller than any ordinary number. And our infinitesimal, it's a very good intuitive concept, very good intuitively. And our ancestors started using it. Archimedes used it and proved some amazing things, and our ancestors continue using them. Leibniz used them. When you talk about dy, dx, you're talking about infinitesimals. Euler, the great mathematician of the 1700s, who basically established modern STEM math, calculus and differential equations. He was it started with Leibniz and then the Bernoullis and then Euler, but he was one of the big ones that did it. He used infinitesimals in his arguments. Infinitesimals are easy to understand intuitively. And the arguments you make, the heuristic arguments, are very convincing and very elucidating. Well, in the 1800s, mathematicians were trying to make everything rigorous. Because it's good to be rigorous because your intuition can go wrong. So they were making everything rigorous. Well, when they got to doing it, they couldn't figure out how to deal with infinitesimals. They couldn't include them in their rigorous axiomatic systems. So what did they do? Well, they banned them. They said, well, since we can't handle them, since we can't figure out an axiomatic system that includes them, they must not be real. They're no good. And they banned them. Unbelievable. Now, this was a great setback for scientists and engineers and mathematicians, too, for understanding calculus and lots of other subjects. Infinitesimals make things so much easier to understand than the things that they use, epsilon delta methods and things like that. The rigorous treatments that our mathematicians developed in the 1800s were much more difficult to understand calculus. Now, here's a great irony. In the mid-1960s, infinitesimals were treated rigorously by a mathematician, and they're back into math again. They're rigorous now. We now extended we created an axiomatic system and a model called hyperreals where they're in. Unfortunately, that was 60 years ago, 50 years ago. Today, even today, calculus books haven't dealt with it properly. The calculus books we use today in high school and even in college are still using the old tools. They don't use infinitesimals. And it's just terrible. I visited an engineering school recently that I knew really well, and I looked at the calculus, and they're still teaching obsolete techniques. And they're not using infinitesimal. Now, there's an even worse thing that's happened. Today, we've developed automated tools thanks to modern technologies. And we can solve a wide variety of math problems that are very difficult to do manually. In fact, sometimes impossible to do with the manual algorithms that were developed by our ancestors. Now, don't misunderstand me. These manual algorithms were wonderful. That's what made our modern civilization, our modern science and engineering. But they're hard to learn, and they're hard to use, and they don't work a lot of times. We have modern tools to solve all that. But guess what we do? In high school and college even, we still make our students learn a lot of these very difficult and weak manual tools. And what that does, it makes the mastery of calculus and differential equations very difficult. And that's the workhorse of science and engineering. So we've created a great barrier, and it's unintentional. It evolved this way. In the 17, 18, and 1900s, we created these tools, these manual tools, that we had to use. That's all we had. We didn't have computers. And they were the workhorses. And so that just meant a lot of students couldn't learn it. It's just too hard. I can't tell you the number of students that flunked out of engineering schools where I taught that because of this, these manual tools. Well, today that's all gone. Now, in tiers 4 through 6 in our training, we utilize these modern tools, and this makes the mastery of calculus and differential equations and a lot of other subjects too much, much easier. You go from a difficulty of 7 or 8 on a scale of 10 down to a difficulty of 1 or 2. Unbelievable. Now, I will also tell you, scientists and engineers, in my experience, rarely care about rigor. They don't care about rigor. They just want to understand the math models so that they can solve the math models that model their real-world projects. That's all they care about. When I taught at engineering school, they tell us how it works. They wanted to know intuition, heuristics. How does it work? They didn't care about rigor. Let the mathematicians worry about the rigor. Now, in my judgment, that's how we should all learn math when we're starting out, intuitively and heuristically. That's the way our ancestors learned it. That's the way it was developed. It's much easier. It's orders of magnitude easier to do it intuitively and heuristically than rigorously. Now, the rigor can come later. If you want to become a theoretical mathematician, you're going to have to learn rigor and how to prove theorems and how to be rigorous. That is a whole different ball game than being a scientist or an engineer. And notice I said if you want to be a theoretical mathematician. Even applied mathematicians don't care much about rigor. Yeah, they give lip service to it, and certainly they are thankful that the theoretical mathematicians have made it rigorous. All scientists and engineers, we give thanks to the theoretical mathematician. You made it rigorous, although you stole infinitesimals from us. I mean, I'm not sure. I'm not sure what that's really done to our development of science and engineering. I think the banning of infinitesimals in the mid-1800s was a tragedy, and it was hubris. Well, we can't figure out how to make it rigorous, therefore you can't use them anymore. Well, bull. We understand them intuitively and heuristically, and they work. They work. We did a similar thing with complex numbers, by the way. In the beginning, we used them heuristically and intuitively, and scientists and engineers, they're indispensable for science and engineering. And it wasn't then later we treated them rigorously. Now, it turns out it's pretty easy to treat them rigorously. By the way, treating infinitesimals rigorously is not easy. It's done, and I studied it, and I kind of understand it, but it's not easy. Well, anyway, if you want to see what we should be doing for high school today, I'm doing this video in 2019. Go to homeschoolertoday.com/math curriculum, and you can download the syllabus for our first 5 tiers. Tier 5 is calculus. And then we have a tier 6 for differential equations, and if you are interested in that, that's not on our website. We only give that out to students that have actually gone through the first 5 tiers. We don't even let them look at differential equations on that. By the way, differential equations, calculus is how you analyze functions. Once you've got a function, it's how you analyze it. And differential equations are how you create functions. That's how you set up math models for science. Differential equations are critical for science. You set them up to model something, and then you solve it and get a function that describes that process. Anyway, if you want to know, you can contact me at craighane.com for that. And what you're going to find out when you look at our curriculum is we actually teach much more math to our high school students than any regular school does. Much more. And that's what we need in this 21st century. If our students are going to compete with the best trained students, this is how we need to do it. Now, you can learn all more about this in a brand new book. This is 2019. I just wrote this book. It's called How and Why Homeschool Math Can Be Vastly Superior to Public School Math. It's the reason I'm telling you about. And the book is, you can read it or you can listen to it. And you can get it for free. Go to vastlysuperiormath.com, and it's free. And you can download a PDF and read it, or you can listen to each chapter. There's an audio. I've done an audio on it, so you can listen to it. Now, notice I said can be fastest. I didn't say is, I said can be. This won't be true if you utilize any of the current textbooks that I call standard math curriculum. Almost everything I've done in tiers 1 through 5. This is from the very beginning, how to use a scientific calculator all the way through calculus and then differential equations. They only use one textbook. Costs $15. It's not 119 pages. George Simmons, Pre-Calculus Math in a Nutshell. But most math textbooks today are obsolete. Why? They're loaded with all kinds of theoretical stuff that you'll never use. And they're loaded with obsolete manual tools, both. It's horrible. If you can show me a 400-page algebra textbook, I will tell you that 350 pages of it are probably worthless. And it's worse than that. It makes math seem much more difficult. If I load you down learning obsolete tools, and I load you down trying to learn theoretical things that you aren't ready for, and you'll probably never use, what's that going to do to you? What if I take the 50 things you need to know, and I add 450 things you don't need to know at this point in time? Either they're obsolete or they're theoretical. What's that going to do to you? Well, that's what this is all about. So that's what this video is about. You can see I get excited about it because our mission at Triad Math is to revolutionize high school math education. And I hope somebody does it. If someone else could come along and do it better than we're doing, that is wonderful. I would applaud that. But so far, I haven't seen anyone else even attempt it. Khan Academy is a good resource if you're studying the standard math curriculum, but I have not seen anyone, including Khan Academy, attempt to really completely redo math. And you have to start with a blank piece of paper. When I started developing this many years ago, several years ago, I didn't start with any textbook. I just started saying, what do our students need to know? Blank piece of paper, use intuition and heuristics, and teach them the things they need to do STEM. Not theoretical math, but STEM. Okay, this is Craig Hane, Dr. Dell. I hope you're having a great life. I'm certainly enjoying mine, and I will perhaps see you on another video. In fact, I recommend you go watch the infinitesimal video because I go into more detail there. It's a great tragedy, I think, what happened. So, okay, Dr. Dell, see you on another video. Bye-bye.